I just want to start by saying that I'm super impressed with the timeliness of the audience here. I got here 15 minutes early, and I was not the first.
It's the lunch tickets, John.
Oh, it's the lunch tickets. That's a great plan. I see. Is that the bribe? They give you lunch tickets if you show up? Does that mean that the food is good or the pay is not very good? Yes. Yes. Okay. So what I'm going to try to do today is give you an overview of the work that's going on both in my group and in collaboration with Dave Schuster's group, making synthetic materials out of photons. So this is sort of a pretty broad field, and of course, making materials out of light means many different things to many different people. So I thought maybe I'd start by telling you what we're not doing. And so you can see people make Bose-Einstein condensates out of non-interacting photons. There's kind of mean field physics from weakly interacting photons. There's 1D strongly interacting gases. There's physics where photons mediate interactions between atoms. There's quantum optomechanics. So why are there all of these very different kinds of things that people call materials that are made out of light that still indeed actually have very little to do with what I'm going to tell you about? The answer is that because photons move so fast, you may have heard they move at the speed of light, there's an incredible amount of room for Hamiltonian engineering. So that is to say, if you look at some of these ideas, the experiments are about, say, mediating interactions between atoms using photons, okay? And the statement is the atoms move back and forth slowly, but you can sit there. That's a good spot. But photons move very quickly, and so you can think of kind of mediating interactions between your atoms with these resonator photons. In that kind of a way, we're going to talk about a different sort of Hamiltonian engineering where we trap our photons in different kinds of structures to control their properties and then make them interact with each other to make materials sort of akin to what people often do with cold atoms. So the two stories that I'm going to try to get through here are making materials out of photons that kind of live in lattices and can hop between lattice sites and interact with each other, and making photons behave like bulk gases in the continuum where the photon has some kind of a mass and some kind of an interaction with other photons, and seeing how that kind of ordering takes place. So these two platforms on the lattice side, this is work that we're doing with Dave Schuster's group, where the lattices are either arrays of superconducting cavities or indeed 2D superconducting circuits. And then on the optical photon side, we're making these bulk gases using multimode optical resonators to make photons behave as though they're in magnetic fields. So, and indeed making them interact as well. And so the pieces of this story that we have to understand are kind of both how to control the single particle physics, okay, and then how to make the photons interact with each other. So for each of these stories, what I'm going to try to do is first give you a taste of the kind of single particle control that we have and how we engineer these Hamiltonians. And then I'll talk to you about how we build many body states on top of that. Okay. So first things first, I'll tell you a little bit about making magnetic fields for microwave photons. So the essential ingredients of this physics is a couple of different kinds of cavities that we engineer. For those of you who are familiar with work from either Ian or Mohammed, you'll see a lot of similarities, I would say, at least in terms of intellectually, how all of this works. So we trap our photons at the bottom of these superconducting resonators. In fact, these cavities can have Qs up to about 500 million, and they don't even need lids, because basically you can think of this as a little coaxial resonator that's evanescently coupled to the outside world. Okay? If we want to couple two of these cavities together, we drill in from the bottom, and now the photons can kind of hop between adjacent resonators. Okay? So just with this, you could think about making a kind of a Hubbard model where the photons can live in the resonators and hop between them. I haven't told you how to make the photons interact with one another yet, but we will get to that. If you want to add magnetic fields to this story, we need one more ingredient, and that is what I'll call a chiral resonator. This is a lattice site in the language of cold atoms that's kind of stirred. Okay? And by stirred, what I mean is that the mode that you can couple to is not shaped like an s orbital. It's shaped like a px plus ipy orbital. Okay? And so to do that for microwave photons, what we do basically is put 3 posts in this cavity so that it supports modes that are, say, x modes and y modes with a node either vertically or horizontally. And then we couple that to a yttrium iron garnet sphere. And that sphere, when you apply a magnetic field to it, only couples to x minus iy, okay, because the electrons in the sphere precess. Okay? And so as a consequence, it splits out these modes, and you're left with only this chiral mode. And the neat thing about this mode is that it has a 2 pi phase winding as you move around the lattice site. Okay, so this is what the whole system looks like. The cool thing about, or one of the cool things about this kind of a lattice is that you design it and then you have somebody else make it for you. And if it's not low enough disorder, you just pay them more money and have them do it again. So let's see if we can understand in what sense this creates a magnetic field for photons. Has everyone heard of the Pyrrole substitution previously? Okay, so we've got 2 people who've heard of it. I think that's probably, no, I'm just kidding. Has everyone heard of the Aharonov-Bohm effect? Yes, okay. So, yes, thank you, Mohammed. The basic statement is we know that in the continuum, what we're used to, if you have an electron and you apply a magnetic field to it, you get a Lorentz force, right, perpendicular to the velocity in the magnetic field. What we'd like to understand is how does a magnetic field affect the tunnel couplings in a kind of tight binding lattice model, right? The easiest way to understand this is through the Aharonov-Bohm effect, okay? And so the basic statement is what you're familiar with is when you go around a closed loop, you take an electron adiabatically around a closed loop, it picks up a geometric phase, right, which is proportional to the amount of magnetic flux that pierces the surface enclosed by that loop. Yes? So it turns out that that is equivalent, enforcing that is equivalent to imposing a Lorentz force. Okay? Now, when you have a classical particle moving around, you may as well just impose a Lorentz force. But in a lattice, it's not clear how to impose a Lorentz force. And so what we need to do is enforce a situation where when a particle goes around a little closed loop, it picks up a phase. And the amount of phase that it picks up is dependent upon the area. It's proportional to the area of the loop that it goes around. And so these little chiral sites here, denoted by the orange to blue with the arrow, are really the key to making that happen. And so the way you can understand this is when I hop from one of the white sites to another, I don't pick up a phase. And I hop from this white site to that white site, again, I don't pick up a phase. But when I hop from this one to that one, well, I can define things such that I don't pick up a phase either. This is what's called choosing a gauge. Okay? I'm going to choose the phase of this lattice site to be 0 at the orange to blue transition. Okay? And so when I hop from this site to that site, I don't pick up any phase. But if I want to hop now from this chiral site back up to the white site, well, I've already chosen where the 0 of phase is for the chiral site, right? It's here. So when I hop out, you can see I've picked up 90 degrees of phase between the entry and the exit point. Okay? And so what that means is when I go around this little loop, my total phase picked up is pi over 2. Okay? And if I go around a loop which is twice as big, well, I'll pick up pi over 2 here and pi over 2 there. And so when you go through this, what you discover is you just have to make sure that each one of these little squares, we call them plaquettes, contains one of these little chiral sites. And this is kind of the simplest pattern that enforces that. And then the amount of phase that you pick up, the amount of Aharonov-Bohm phase, is equal to pi over 2 times the number of plaquettes that your trajectory encloses. Okay? And so we make this object. And what do we know happens when you apply a magnetic field? Well, we know you should get cyclotron orbits, right? But if you're at the edge, if you're in the bulk, you get nice little round orbits like that. If you're at the edge, you should get hopping orbits that go around the edge of your system. So we do this experimentally. This is the band structure that we expect for the experts, and these are these edge channels. And when we measure, what we discover is that we get exactly the band structure that we expect, along with these edge channels at precisely the predicted energies. And indeed, if we put an excitation into the edge of the system, this is a movie measure where we measured each lattice site in real time and watch how the excitation moves, and indeed it just moves around the edge. So this all works kind of as we would expect it to. The other story I want to tell you on the microwave side is how to make these photons interact. The long-term game is, of course, to combine these two things and make topological materials where we have both interacting photons and these effective magnetic fields. But as a starting point, we will just talk about making photons interact. So, yes?
Could you say something about whether or not it matters if the chiral sites are on the edge or not?
So you're saying, why have we arranged the situation?
I was just curious if it matters where you cut it with the edge.
It does not. So it matters in one way, which is when you measure this band structure, the quasi-momenta of the edge modes is determined by where you cut, right? But you can also kind of change the quasi-momentum of the edge modes based upon how you measure. So in some sense, the gauge invariant things, which are things like how much power do I have at each site as a function of time, are independent of whether there are chiral sites on the edge.
Do you ever reverse the magnetic field and do it backwards? Or is it always, does it have to go, is it designed to go one?
So here's what I can say. If you excite in the lower gap, it goes one way. If you excite in the upper gap, it will go the other way.
Right.
Now, you're saying, why don't we excite in the lower gap and then flip the magnetic field? Well, the way this thing is actually implemented is we have a rare earth magnet placed beneath each one of these chiral sites. So flipping the magnetic field is kind of a pain. And the reason for this design, in fact, is that magnetic fields don't play so well with superconductors. So in fact, what I've shown you just now is just room temperature, right? But when we want to get a factor of 100 to 1,000 in Q, and we want to add interactions, we want to only have magnetic fields at the locations where we really need them for this magneto-optic effect. Okay? Yes?
So if I chain a bunch of circulators in a lattice, would the physics be similar?
What an interesting question. I think the fundamental answer is there are ways to put together circulators that give you nearly identical physics. Because, of course, circulators are made of these little Yig spheres, right? The challenge is how to have a circulator that's high Q, right? Or that is to say very, very low insertion loss. So what we've done in some ways, the circulator designs are typically optimized for bandwidth rather than insertion loss. So we've optimized for very low insertion loss rather than very low bandwidth. But yes, you can think of this as a lattice of high Q circulators.
What are we looking at here? I mean, there's a lot of information that it seems like you have in total. There's blues and there's reds and there's
There are too many slides, I think, is what we're really looking at. But so let's go. So what are we looking at in this picture? So the deal is you can look at these sites, okay, and the ones that are white here are the ones with the single post in the middle. And the ones that go from orange to blue are the ones with 3 posts in the middle.
Right, but I guess what I'm thinking is the ones with single posts look more complicated than a single post.
So what is the black thing in the middle of that?
Maybe that's what I'm asking.
Yeah. So
the blue or the red in the other picture?
So the blue and the red in this picture are just whatever's behind.
On a checkered table.
So I try to get the students to do things on a white background, but you know they'll do what they'll do. So this is the ocean here that you're seeing, and that's the sun. But no, you have actually hit on something interesting, which is that these ones are a little more complicated because we have the ability to tune their frequency to correct for disorder.
I see. So there's sort of a plunger in there.
Mm-hmm. Which is not really fundamental, and then if we move back one slide, so that's these, and then the student was paranoid that the tunnel coupling wouldn't be uniform enough, so there's also a screw to adjust each tunnel coupling. Again, you know, without that you get accuracy of about a 20th of the tunneling energy, just by default.
Okay, so the tunneling coupling is just like a coupling hole between cavities.
That's right.
With the same kind of screw that you would have if you were making a tunneling coupler for a whole coupled cylinder.
Exactly. Yes. Yeah.
Okay.
The screws need to be a little lower loss, but so they're aluminum, which is miserable. But yeah. So the second half of this story, is that was kind of nice. The second half of this, I see. The second half of this story is how to get interactions between the photons. And so for this, I'd like to just quickly make the analogy to cold atoms explicit, okay? So if we have cold atoms in a lattice, we make the lattice with some laser field. And the atoms can then live in each lattice site in kind of the lowest harmonic oscillator state and tunnel to the next lattice site. This is our hopping procedure. And then 2 atoms on the same site can collide with each other, right, through some S-wave contact interaction. The analogy that I want to make here, we're going to replace, for now, this optical lattice with an array of transmon qubits, okay? And the tunnel coupling is replaced with a capacitor between adjacent transmons. Okay? Now, here's the thing that's funny. When I say qubit, you think of a 2-level system, right? The problem is what I've drawn here is not a 2-level system. So the question is, what does this actually have to do with a transmon qubit? Well, the key point of these transmons is that you can engineer a 2-level system by ignoring this 3rd level. What is it that allows you to ignore the 3rd level? Well, it's that the spacing between the lowest 2 levels is different than the spacing between the 2nd level and the 3rd level, right? So that allows you to treat this system as a qubit. You can drive transitions between the lowest level and the first excited level, okay? In much the same way you can treat an atom as a qubit because you can excite it from the, say, for rubidium, 5s to 5p, right? But 5p to 5d or to 6d is at a very different energy, so you can just drive transitions on that 2-level system. So what we're going to do, though, is take these transmon qubits, which were developed for quantum computing, and directly harness this third level, okay? And so the statement basically is, if you think of this transmon as a harmonic oscillator, or an anharmonic oscillator, that it can hold 0 photons, 1 photon, or 2, like a lattice site in an optical lattice, okay? The interaction energy between the atoms is the difference between the energy for 0 photons and 1 and the energy for 1 photon and 2. Yes, so this anharmonicity maps directly onto the Hubbard U in a Bose-Hubbard model, okay? And so essentially, we can build a lattice of these transmon qubits and just couple them together with capacitors and get a Bose-Hubbard model. So very quickly, to give you a sense of the energy scales, our U is typically on the order of 200 megahertz. Our J is on the order of 20 megahertz. And the photons live for about 50 microseconds in our highest quality samples now. So these numbers are very much in line with the sorts of things that you get in a cold atom experiment with a prefactor of like 100,000 or 1 million, right? But their ratios, which determines how much entanglement, how much ordering you can get, are pretty similar. Okay, so the challenge now is we've got a Hamiltonian that I claim is the physics that we want. It's got the tunnel coupling, it's got the interactions, and we could talk about how to do those experiments. 1 second, then I will get to yours. But you can just believe me that we have that Hamiltonian. The question is, how do you build the many-body state? Jake?
It looks like the sign of U is wrong.
The sign of U is wrong in this picture.
Okay.
I don't want to confuse people. So this is a negative U Hubbard model. It's also a negative J Hubbard model. But the sorts of stabilization techniques that we're using are agnostic to that. Thanks for nothing. It's a good catch. But if the states get more squished together, it just doesn't look as nice. So imagine we want to prepare the many-body ground state of this system. As Jake has pointed out, maybe it's the many-body highest excited state, but be that as it may. Yes?
Can you explain again, what's the ground state in the sense of using the photons? Because I'm more familiar with atoms or electrons.
So let me ask you this. You're worried because the photons can decay, right? But what I'm telling you is the ratio of the interactions to the decay rate is the same for our photons as it is for your cold atoms, right? So if you're comfortable with the model for the cold atoms, you should be comfortable with the model for the photons. What I think this gets at is this challenge of how you prepare the states for cold atoms. What's the game there? The first thing you do is you laser cool your atoms, and then you evaporatively cool them, and you make some Bose-Einstein condensate, right? Which is a very low entropy initial state. And then you adiabatically change your Hamiltonian, and for however many particles you have, since you were in the lowest energy or near the lowest energy state for your Bose-Einstein condensate at that particle number, you end up near the lowest energy state for your cold atoms in the lattice at that particle number, right? The real lowest energy state for the atoms is, of course, a bunch of rubidium-3 molecules or something sitting on the floor, or ground state rubidium-2 molecules, right? But if we're assuming that they're atoms and that they're required to stay in the trap, this is the effective ground state. So the same statement is true here for the photons, but the challenge is that this adiabatic transformation protocol is much harder for photons than it is for atoms. As Bill pointed out, if you wanted to adiabatically go from a superfluid to a Mott insulator, you'd have to adiabatically tune all of those little screws in the lattice. And we have a lot of graduate students, but not that many, and they can't turn the screwdrivers that fast. No, we didn't try that. And look, there are ways around this with Josephson parametric couplers between the sites for the experts, but it becomes much more technically demanding to do it that way. So the game, and I think in some sense this was originally framed by Jake some years ago, is to develop either a chemical potential or more broadly some way of dissipatively stabilizing a many-body state of the photons. Okay? So let's make a picture kind of qualitatively of what I mean by this. So I've got a bunch of water here.
Can you just repeat the numbers once more?
Yes.
For the energy scale?
So U is about 200 megahertz. J is about 20 megahertz. And the lifetime is about 50 microseconds. Okay? So that means that we've got something like 10,000, well, 2 pi 10,000, maybe 60,000 tunneling times, right? So I mean, the numbers are quite good in that regard. Okay, so I've got a liquid here and I've got a bowl. I pour the liquid into the bowl, and I get what looks like the ground state of this fluid, right? Well, initially it had some waves on it, but if you wait long enough, they go away. So the question is, why can't I just do that for my photons? I'm just going to pour some photons into the bowl, right, and let them equilibrate in their ground state, such as it is. Well, where did the energy from the waves go? Well, it went into heating the fluid. Maybe it went into sound. Maybe it went into the air. It went into dissipation channels, right? But the whole point is we've worked very hard to not have dissipation channels in our system. You know, Mason asked me to repeat the numbers. You know, we have 60,000 interaction times. We have maybe 6,000 tunneling times, right? So we could add dissipation everywhere, potentially couple it to something else that can take away some of the energy. But if the whole point is to study, you know, how the particles become entangled, how they move around in the system, in the absence of decoherence, you don't want to do that, right? So then what we'd really like to do is make some system that doesn't have internal damping, okay, but where we can pour it in and all the entropy can leave out of a little hole in this corner, right? And we want it to be a little hole, and we want it to only be in one corner, because the statement is that then we can have this hole open for all the entropy to leave. And then when we're done, I put my finger over it, and we get quantum coherent dynamics of the fluid after that. So the question is, how do we engineer such an object? So Jake has a very sort of general way to do it. We have a specific implementation which works only for incompressible states, which is kind of more akin to work that you guys have done with Mohammed and Elliot. Actually, it's exactly equivalent to that, but maybe a little simpler to implement. So, oh, there we go. So the basic idea of this approach is to take our Bose-Hubbard chain here and couple it to an object which can only hold one photon and is continuously optically pumped into that one photon state. Okay? So first I'm going to tell you how to make an object which always has one photon, even right after you take a photon away from it. And then we're going to get a sense of why this is the right thing to couple to this chain. Okay? So the basic idea is we need to implement some optical pumping. We need to invert this system. So anyone who's ever studied lasers knows that the key is to excite the system from this lowest level to some higher lying level, right? And make sure that that higher lying level decays, 100 or 1,000 times faster than the state that we want to stabilize, right? And so you excite it to the higher level, and then you let it spontaneously decay into the state that you want it to be in. And then it'll live there, and as soon as the photon's taken away, then the system is, the laser that excites us from 0 to 2 is still there, and the system's immediately re-excited. So the point is, for our transmons, this 2 state, which we use over here to get our Hubbard U, lives about half as long as the 1 state. And we would like, a factor of 100 or 1,000 difference in lifetime. So what we do is we Purcell enhance the 2-to-1 transition by coupling to a lossy resonator. Just a low Q resonator which is tuned to the 2-to-1 transition. Okay? So this is going to be our little hole where entropy can leak out, as you'll see in a moment. So this whole object now, I'm just going to draw as this blue thing here. And so if this transmon is ever in the 0 state, it's optically pumped through the 2 state to the 1 state. And if it ever ends up in the 2 state, it's optically pumped to the 1 state. OK, so what happens when I couple this to my chain? Well, let's turn on the system. And we're immediately populated in the 1 state, right? That's what we said this object does. No matter what, it tries to put 1 photon into this transmon. Now that photon tunnels into our chain, right? Because we've tuned it up to be resonant with the chain. Great. Then that site immediately repopulates itself, right? Because that's what it does. Now, can this photon tunnel into the chain? No, because there's an interaction energy cost U. Can this photon tunnel back into our photon source? Also no, right? So things look to be in a stalemate, except that this photon can hop over by a site. And as soon as it does that, this one hops in and the thing refills, right? And basically, this fills up your system. As long as there are states at the bare energy of this cavity, you'll be able to eventually populate them and stabilize your system in this Mott phase. So what you can see is that this process is kind of not reversible, right? So where did the entropy go? Exactly. That's the only place it can go, right? And so that's how you know, for this kind of a protocol, we talk about dissipation, we typically think of it as a bad thing, right? But if you want to prepare this many-body state, you need a place to put your entropy. And so it leaks out through this cavity. Interesting fact, and this is the reason that we think this approach is so powerful, fractional quantum Hall states are also incompressible, in the sense that you can put photons into the system, or electrons, or what have you, and it costs you 0 energy to do so, right up until you fill up to the fractional quantum Hall state, and then there's some energy cost to put in the next particle, right? Here the energy cost is U. In the fractional quantum Hall state, it's whatever the many-body gap is, right? So this kind of an approach, in principle, works for stabilizing fractional quantum Hall states, and that's the context in which Mohammed and Elliott developed their protocol. So, yes.
What happens if you have, like, these things go in a 2D lattice and then you have a whole bubble trapped over there? And if there's some disorder, any amount of disorder, the bubble just stays there and doesn't come out there?
So,
or it takes a very long time to come out?
So there's a question in higher dimensions, right, and in general, actually, of how many of these thermalizers you want to put in, right, and how you should position them across your system, right? And I think it's actually sort of an interesting thing. You can ask what the steady state is as a function of how hard you drive these things, right? And if you thermalize just in a corner, as long as the lifetimes are really good, and they may need to be exponentially good, but I think it's usually polynomial, you get kind of in the bulk the many-body state that you want. But if you have too much loss, then you need more of these things. And remember, in some sense, this thing is constantly making a measurement of the occupation of the adjacent site, right? So if I think there's a whole sort of non-equilibrium thermodynamics that needs to be developed for this that asks, this thing stabilizes a many-body equilibrium state or density matrix. What does it have to do with the many-body ground state with that number of particles? And we don't really know, except for the Mott insulators, where it seems to work.
I guess the bulk also has some loss, so that helps you.
I wish it had less. right?
Yeah.
I think this is the basic statement. If that loss is not the good kind of loss,
No, but
right?
if I have a defect that's stuck there, it won't
Yeah.
be there forever.
Yes,
It'll
yeah.
get out. Yeah.
Although, of course, the game is if the bulk had less loss, then you could drive less hard, right? And so in general, you want it to have some, but less is always more. Okay, so this is a 4-site Bose-Hubbard chain, as you can obviously see from the picture. This one, I know Bill would be very sad if I didn't give a little more detail this time. The last one was maybe excusable. So these are 4 transmon qubits. You can see that because they look like little T's. And they're capacitively coupled to one another. So we're not going to talk about how transmon qubits work internally. They're basically LC oscillators, where the L is a nonlinear inductor coming from the Josephson tunneling through some very narrow oxide layer. But just think of it as a nonlinear LC oscillator, but nonlinear at the single photon level. So there's capacitive coupling between the qubits. These bias lines allow us to tune up the frequency of the individual qubits to make the lattice sites all the same energy. And these are readout resonators that allow us to measure with high fidelity the occupation of a single lattice site. So you can think of this as a kind of microwave quantum gas microscope here. But it's a little quantum gas microscope. 4 sites. So this is very, very preliminary data. As was pointed out the last time I showed this, it's even uncalibrated, although the calibration is coming very soon. But this is the 4 sites as a function of the time since we turned on the thermalizer. What we know now is that it's between 0 and 1 photons. I think this is in the neighborhood of 0.8 to 0.9, but I don't have a definitive number for you yet.
Say a little bit about how that's measured.
So the basic game is, as soon as you start to measure, so these cavities, when we do cavity QED experiments, you can measure the state of an atom inside of a cavity based using the shift of the resonator, right? I don't know, has everyone studied the Jaynes-Cummings Hamiltonian? No? Okay, I know you have. Everyone has, okay. So the basic statement is that depending on the state of this qubit, the cavity moves to a different frequency, okay, by, say, a megahertz. So these cavities are different in frequency individually by 100 megahertz. So we can do frequency multiplexing and measure each of their frequencies simultaneously, okay? And so what we do is we let the system evolve coherently for some amount of time, and then we make a projective measurement by sending a lot of light into each of these cavities and measuring its frequency, okay? So yes, if you try to measure this whole curve continuously, of course, then you don't have quantum evolution while you're doing it. I guess that was maybe what you were asking.
Yeah, so each one of those things represents a repeated measurement after a certain evolution has occurred coherently. Then you make repeated measurements, and that tells you the average of the number of, because when you measure it, you either get a photon or not.
Exactly.
So that's the average.
Yes.
Of many measurements.
And in fact, you could do it the other way if you really wanted to and measure hard, but then you would quantum xenosuppress the occupation of the chain. Yes?
So you say this is an application of your protocol. I'm kind of curious which one of those 4 sites is the one that's your leaky one? In the device. You have one site you're doing this 2-photon drive on. That one.
And that's the lossy resonator right there. So I should have pointed that out. As you can see, it's very lossy.
Is that like a blob of oxygen deposited by a student that's about material?
No, I mean, I think the point is so the Q of this resonator is determined by the capacitive coupling to this 50 ohm transmission line. So this guy is just more strongly coupled.
Okay, but not so bad that you can't measure it.
Yes, exactly.
And that's the one that you're also calling a 2-photon drive. And how do you apply the 2-photon drive only to that transmon?
Yes. So This is an interesting question. I mean, it does have its own line, RF drive line coming in, so we can just drive it directly. Now, to what extent does that drive the other ones is a bit of an open question.
But presumably they all have slightly different U's, right?
Yes. Well, yes. I mean, they're designed to have the same U, but they have to be biased differently.
Yeah.
So it should be okay. And it seems to be.
Apparently it is.
Yeah, yeah. Well, I mean, I think there is some question because I think we now have in the mid-90s, I don't want to be nailed down to that, but if you look at the numbers, you should get 99-point-something% fidelity, which we don't have. And there's a question of, is that coming from not driving the site that you should be driving, or is it coming from some 1 to 3 coupling? So it may be that you're right, that there's some residual coupling that shouldn't be there.
Will you be able to measure correlations between sites?
So this is the thing. Because these are at different energies, we can make measurements of every site simultaneously, right? And they're not kind of mean occupation measurements. In a single measurement, we know the occupation of the individual site with 95 to 98% fidelity or something. So it really is, in some sense, like a quantum gas microscope.
But now, drawing the analogy between this data and the cartoon above it, I would have thought that as time progressed, that I would see the occupation of these sites sort of spread from its source to the end, and that doesn't look like what's happening.
So the statement is basically that the optimal parameter regime is. Do I have a good answer to that? I think I was going to say something which isn't true. I was going to say you're filling the different quasi-holes at different energies at different rates. But I think the point has got to be that those have got to add up coherently to give you something that moves outwards. Now, why is that not the case here? I don't have a great answer yet. But I would say I certainly expect to see that to some extent ultimately. Now, I think one can say this. You have to be driving the chain. Yeah. Here's what's going on. To see what you want, you have to be sort of thermalizing the chain very fast compared to J.
Okay.
Right? And you can see that that's actually not a smart thing to do, because if you thermalize the chain fast compared to J, you're kind of xenosuppressing this photon tunneling to the next site, right? Because it tries to tunnel, but as soon as that happens, this one tunnels in and a photon leaks out. So you're making measurements of this occupation too often, and it suppresses the filling rate of the chain. So I think the point is when you run the numbers for the optimal filling rate, it's kind of slow compared to J, and so you don't get to see too much of that. Now, our new sample, and this is what I was going to say next, goes from this 4-site. Oh wow, can you see anything in that picture? Not at all. So there are actually 8 transmons. Oh, you can see the 8 transmons at least. The new sample is 8. So I think the point is, at some level, once the chain gets long enough, even if your repopulation rate is small compared to J, you'll be able to see the thing propagate away.
Now, as with 4, this 8 thing, it looks like the 2 on the end have a different.
Yeah.
So what's going on? What are you doing?
So this is an interesting thing.
Do you want to talk about the second part?
I'm not going to talk about the second part. That's okay. So the basic statement is that tunnel coupler has been designed to be about a factor of √2 larger than the other ones. And the reason is that the simplest way to think about this repopulation process, you have a full chain, okay, and then you lose 1 photon, okay? I would like you to think about that in quasi-momentum space rather than in real space, because that means it has a well-defined energy, okay? You just have a hole band, And if you lose one,
I lose an electron from, or not,
Yeah.
an excitation from a quasi-momentum state rather than from a site.
yes. And you're kind of, I mean, unless we've measured it,
I'm
you're,
allowed
yeah.
any
Yeah.
spaces I want.
Yes. So that one's nice because the refilling process kind of knows about energy. Okay? And so what you can see is in this quasi-momentum basis, you need to be repopulating on the order of J, right? Otherwise, you won't refill all of the quasi-holes equally. Yes? But there's another requirement, which is kind of what is the matrix element overlap between this thermalization site and quasi-holes at different quasi-momenta. Yes? Right, we're repopulating from the end of the chain.
Yeah.
So you could imagine that some of the modes actually have zeros at the end of the chain. Right? And that would be a problem because then you wouldn't be able to repopulate those. So you could say, well, let's put multiple thermalizers in. But if you want to make it as simple as possible, it turns out if I think of a chain of length 2L and I fold it over on itself, okay, then this middle site, so then I can look at only the symmetric modes of this thing, right? The middle site is coupled √2 times more strongly to each of the neighboring sites, and it has the same matrix element overlap with every site. And so,
So you engineer that.
so you just make it closer together, and that.
So you said, but that's just what I'm seeing is a bigger capacitor between the one on the right and the one next to it.
Yes. That's all you wanted. I apologize. I thought this was cool.
No. I mean, no, I'm not.
Yeah.
I have all the rest of that too.
Very political. So anyway, this first sample, and this is a piece of the reason why the performance may not have been as good, only had a 5 microsecond lifetime. This new sample that we're playing with now has a 50 microsecond lifetime for each of these qubits. And so the essential game moving forward here is to kind of combine these two ideas, okay? Replace the single post cavities with transmon qubits, 3D transmons, and put one in each of these cavities. In fact, what we've shown is that you only pay a factor of like 3 or 4 in your many-body gap if you only have transmons in 3 out of every 4 sites, right? You can still create some topological many-body state in this system. And so this is kind of where that effort is going. So these are my collaborators on that piece. This is Dave Schuster, who I'm sure most of you know. And this is Brendan Saxberg, who's the new graduate student on it, and Alex Ma, who most of you have probably met at DAMOP. He was Marcus Greiner's grad student. He's really the guy he's a postdoc. He's taken the lead on this effort and just done a great job. So at this point, we need to make an executive decision. 10 minutes. 10 minutes and only, why does this always happen? And only 28 slides. So I think what I will do is not tell you anything about how to make optical photons interact, okay? But I will tell you briefly about in what sense we can even think of optical photons in a multimode cavity as massive harmonically trapped particles, and maybe how we can make magnetic fields for them. Yes, Ian has seen how this can go. So the central premise here is that a photon in a multimode resonator behaves like a massive particle in a harmonic trap. Now, what this story is not is the story that you heard in your first quantum field theory class. In that class, you say, I have a single mode, right? And I can put 1 photon into it, or I can put 2 photons into it, or I can put 3 photons into it. And there's a bosonic commutation relation there, which is associated with a raising operator, right? Here I'm saying actually something different. I have a cavity with multiple modes, and I'm only going to put 1 photon into it, but it can be in the lowest harmonic oscillator state, or it can be in the first excited harmonic oscillator state or the second excited harmonic oscillator state. Spatially, right? So the question is, what am I talking about? But I want you to start by being confused so that you're not misinterpreting it. Maybe a little too hostile. I don't want you to start by being confused. I want you to pay attention. How about that? Okay, so I'm going to send light in off-center to this two-mirror cavity. Okay, and we're just going to, what I'm going to claim will happen is if you watch the wave packet, it oscillates back and forth transversely in the central plane of this cavity. So you can see how this kind of happens in a ray optics picture. We just watch the ray, and if you kind of coarse grain and only look in the central plane, you can see that this ray is kind of oscillating back and forth like a massive particle in a harmonic trap. So if any of you have ever played with lasers, maybe a couple of you, you know that the modes of a Fabry-Perot cavity are Hermite-Gauss wave functions, right? And they're uniformly spaced. And they are uniformly spaced in energy, right? Those are the same wave functions of a quantum harmonic oscillator, which are Hermite-Gauss and uniformly spaced in energy. Okay, and so what this now says is if I send light into my resonator off-center, I can write that photon or that optical field's wave function as a superposition of the lowest mode of the resonator, right? And the first excited transverse mode, okay? Because these two will constructively interfere on the right side and destructively interfere on the left side. But if they're at different energies, because the cavity has some transverse mode spacing, a little while later, this first excited transverse mode will evolve a minus sign relative to the lowest mode, and now I have a photon which is off to the left side of the cavity. Okay? And so the picture now is something that you've learned in first-year quantum mechanics, right, for how a particle in a harmonic trap behaves classically, right, even in this quantum picture. And the picture you should think of here are my two mirrors, and the photon is delocalized everywhere longitudinally, because I'm not talking about the different longitudinal modes of the cavity, right, just the different transverse modes, but it oscillates back and forth transversely. So the reason that we don't normally run into this when we think about cavity quantum electrodynamics is that normally we're thinking about only a single mode of the optical resonator, right? And the game that we're starting to play in my group is to say, if we have ways to make strong interactions between the photons, and now we do, let's think about adding multiple transverse modes to the story and seeing what kind of physics comes out, right? And it turns out it's physics which is very akin to what you see in a cold atom experiment. So the way to think about this physically is that the mirror curvature is kind of trapping the photons, right? They would just bounce back and forth off to infinity, except that there's mirror curvature to kind of refocus them back. So that corresponds to some harmonic trapping. And the free space propagation of the light kind of means that a tilt in the beam results in a translation after a round trip. So that's kind of like the photon mass, okay? And what you can see is that each of these is a term which is quadratic in either x or p, right? The free space propagation gives me something which goes like p squared. The mirror curvature gives me a term in my Hamiltonian which goes like x squared. So the natural thing to ask is there a way to get a term that looks like xp, right? That's what a magnetic field looks like in a Hamiltonian. And the answer, it turns out to be yes. You just need to twist the cavity. So how does one understand that? The basic idea is that when I twist the cavity out of the plane, on each round trip through the cavity, the image gets rotated a little bit, okay? And you can understand that by thinking about a periscope. So what I've drawn here is two mirrors, okay? And I'm looking at a tree through this periscope. So if I align the mirrors to one another, the tree comes out right side up. But what if these two mirrors are 90 degrees off from one another? Well, what you can see is that the tree comes out rotated by 90 degrees, right? And in fact, the angle of rotation between the two mirrors determines how rotated the image of the tree is. And so what the cavities I'm going to describe are is basically a twist like this, and then two more mirrors to close the thing into a resonator. Okay? And so the way you should now think of this is on every round trip through the cavity, the rays get rotated a little bit, and that turns the lab frame into a rotating frame. So what do we know about rotating frames? Well, we know that we get a Coriolis force and a centrifugal force, right? But this Coriolis force looks a lot like V cross B, right? In fact, it has the same form, just a different prefactor. So that Coriolis force actually gives us a Lorentz force on our photons. And all we have to do is cancel this centrifugal force, which looks like a radially outward force, with mirror curvature, which gives us a radially inward force. Okay? And so in deference to lunchtime, I will just say that this works very nicely, except that what we discover is that our photons kind of live on the surface of a cone. But more importantly here, we can make these levels degenerate to a megahertz or better. So we get a Landau level here when we cancel the harmonic confinement. And this megahertz kind of energy scale is exactly the energy scale that we need for well, I guess it's not exactly. It's small enough that Rydberg interactions can overwhelm this and produce topological many-body states. So that's where that piece of the story is going. So on that note, I think I will just thank my group and Dave Schuster and his group and ask you guys for questions. So, thanks.
Maybe a short question, and then I remind everyone 4 p.m. there is the tea students and sometimes with maybe one question.
Okay, so first of all, I really enjoyed the talk, and obviously the results are beautiful.